So 19, I'm sure you've noticed, it's basically all new functional groups. Some of these you probably never heard of. I don't think many of them were discussed in previous chemistry classes. But the main functional group
Carboxylic acid.
Good. Okay. Be careful. Really make sure you're not mixing these up with ketones and aldehydes specifically. In terms of priority, so when we are naming things with multiple functional groups, okay? When we talked about aldehydes and ketones, I said that they have greater priority over, say, if we're looking here, right? What would have the highest priority?
The carbonyl.
Yep. Second priority?
Alcohol.
Good. And then something else. So that could be an alkyl group or a halogen, something like that. Carboxylic acids take precedent over carbonyl groups. Okay? It's more oxidized. So here we have 2 carbon-oxygen bonds. Here we have 3. So this is always first priority with the ones that you're going to be working with, okay? You're really not going to see something that's going to take a priority over carboxylic acid, okay? Let's talk about naming. Can you name this one for me?
Okay. It's an aldehyde.
Oh, sorry. There we go.
Okay. So it could be one of 2 names, right?
So let's do IUPAC first.
Okay, so propanoic acid.
Good. So with IUPAC, the ending, oic acid, everything else is the same as, how you would name a normal alkane. You're just changing the ending. Do we have to say where the carboxylic acid group is?
Not unless... No, it's terminal.
It's terminal, so it's always going to be 1, always.
Yeah.
Okay, so you talked about common names. So what are the prefixes for your common names? Not IUPAC.
Like acetic acid?
Okay, so and how many carbons does acetic acid have?
2.
Okay, so acete is that prefix, okay?
Oh, just go straight to acetic acid.
Well, it's good that you know that one. This is really going to be the only common name you're going to be asked about, specifically acetic acid, because it is so common in organic chemistry.
Mm-hmm.
We can do, since we're talking about carboxylic acids. So form, acete, propion, butyr. Okay, those are the prefixes for common names. Like I said, acetic acid is really the one that you need to know. I wanted to do, oh, here we go.
Benzoic acid.
Very good.
I don't know why I just made a face like I didn't know that.
Well,
I said,
but even if you're not 100% sure, you can take what you do know and make your way towards the correct answer, right?
Yeah.
Okay, what about...
Okay, so that's an anhydride, right?
Close. Anhydride actually looks like this. So there's an oxygen in the middle, not a carbon. Okay. So obviously we still have our carboxylic acid group.
Yeah.
What's that?
Would you do 1, 3, or?
So it's actually if something has two of the same group, what do we add to the name to indicate that there's two of the same group present?
Oh, di. Oh.
So this is part of a class of dioic acids.
Yeah. Okay.
Okay. If he did want you to name it, okay, the prefix is going to stay the same, right? There's still only 3 carbons. So propan, dioic. Again, we don't need to put numbers with this because a carboxylic acid is always terminal. So if there's 2 carboxylic acids, they're going to be on each end of that alkane, in a sense, of that molecule. So propandioic acid.
Yeah, he didn't really go over naming these ones.
He is probably assuming that you know carboxylic acid. Which I don't really know why, considering he kind of went into all the other functional groups, right?
And we never talked about it in any of the other chemistries.
Oh, you didn't?
Dioic acids.
Oh, dioic, yeah. This is definitely building on top of it. He may or may not talk about this one. I just like to throw it in there because it is up for grabs technically, as is benzoic acid. I think those are technically the ones that kind of, you forget about. Honestly, if he's going to talk to you about a carboxylic acid, it's probably going to be ethanoic acid, otherwise known as ethanoic acid.
So there's
acetic acid, right?
Oh.
Okay, so I have a feeling you're going to hear that one just because, again, it is used so commonly. I mean, even in Dr. Cosper's notes, 2 million tons of acetic acid are produced annually. Extremely important industrial chemical. Be certain you know the name and the structure of acetic acid.
Okay.
So if I asked you to draw acetic acid, would you feel comfortable doing that?
Let me do it just because.
So good, 2 carbons, carbonyl carbon, and an OH group attached to the same carbon. Perfect. I'm just going to keep like a running tally over here of the functional groups that we talk about.
Okay.
There's going to be lots in this chapter. I know I've already said it a few times, but if you haven't already started keeping a comprehensive list, this would be the time to do it. Okay, so let's talk a little bit more about the carboxyl group. Would this be polar or non-polar?
It's polar.
Polar, good. If we're looking at this center carbon, sp1, sp2, or sp3?
sp2.
sp2, good, because we would have 3 different attachments, right?
Mm-hmm.
Okay, spp, sp2. So similar to, I think this was, I'll just do it. So this hydrogen is very acidic. So it is really readily removed, okay? So we can have, Once it's removed, that creates a charge, which kind of opens up the space for reactions to take place. So keep that in mind. Okay, if we had,
I have a question.
yeah,
Okay, so if that hydrogen is removed, how come in the what reaction was it? I don't know, but it's on the second page.
the acidic
point
basic.
C.
Yeah, so we're gonna get to that. So basically, there's acidic and basic properties. So this one can kind of act a little bit like both. It definitely is more acidic than it is basic. But the point that you're talking about is referring to when it does act like a base, what occurs.
Oh.
Okay, so definitely more acidic. It's not considered a strong acid necessarily, but in Dr. Cosper's notes, for example, she says a relatively strong acid. Okay, but it does have some basic properties, so we will get to that. That's a good point. So if we have acetic acid, would you think this would be soluble in water?
Yes.
Okay, is there a limit to the solubility of carboxylic acids?
5 or more.
Yeah, so under 5. So
Oh,
1
yeah,
through 4. It's
yeah.
exactly the same as alcohols. Okay, so anything above 4, so 5 and higher, would be not soluble in water. Okay, very good. Wanted to do a little bit of an exercise with boiling points really quick, just to kind of review since it's just you and I. Okay, so we have 4 different compounds. Which of these do you think would have the lowest boiling point and why?
The alkane,
Okay, so which one's the alkane? Let's,
the second one.
okay. Okay, why would this one have the lowest boiling point?
There's no hydrogen bonding.
Okay, what type of bonding is there?
Just the weak forces. Van der
Waals or London dispersion. Good, excellent. Okay, what would have the next highest boiling point?
The aldehyde one.
Okay. Next.
Alcohol.
Okay, why did you make the decision to put this one below this one? What's different?
Alcohols have very strong hydrogen bonding, where aldehydes don't have hydrogen bonding.
Good. So what type of bonding is different from these two? So this one has London dispersion.
That is dipole.
Dipole, hydrogen bonding. Okay, so that means you left the carboxylic acid. Okay. Why is the carboxylic acid higher than the alcohol?
Because it has the dipole and the hydrogen bonding.
Good try. So hydrogen bonding, remember, is a type of dipole. Okay, so
Yeah.
technically you already have both. So the reason why, but you did really, really well. So I'm gonna draw. How she had it. Okay, so if we have 2 carboxylic acids in close vicinity to each other, we actually have the ability to make 2 hydrogen bonds. Okay, this is referred to as a hydrogen bonded dimer because there's 2 of them. So we have the carbonyl group of 1 kind of attracted to the hydrogen off of the OH group, and then you have the same thing happening here. This differs from alcohols. I'm not drawing this right. Not the best drawing. Alcohols can only really have one hydrogen bond. Okay, so carboxylic acids and alcohols have the same type of intermolecular attraction, but this one is able to have two. Okay, this is similar to water. Okay, so water can also make this. So just to kind of show you the actual, so this alkane has a boiling point of negative 88 degrees Celsius. The aldehyde is 21 degrees Celsius. 78.5. 118. This is actually the first, I believe, compound that has a higher boiling point than water. Okay? So the two hydrogen bonds, you have to also remember this has more molecular weight, so it's a heavier, so that is also going to play into the boiling point. But water can have two boiling points, has a very high 100 degree boiling point. Acetic acid also up there, 118, because of the two hydrogen bonds. Okay? Probably not going to get a question on this, but I think it's important to kind of keep up to date on that.
Yeah.
Any questions on any of these? Feeling okay? You did great. Okay.
I knew it was higher than alcohol, I just didn't know why.
Yeah, yeah.
So.
You got those easily. I was surprised. Sometimes that's the stuff that gets lost by the wayside. Switching gears a little bit. If we were to run this through the NMR, okay, would this carbon and hydrogen be deshielded or shielded?
Deshielded.
Why?
Because of the oxygen's electronegativity.
Exactly. Anytime you have electronegative atoms, it's going to deshield the surrounding carbons and hydrogens. Very good. Okay, so this brings us to the acid-base kind of talk. So let's review the acid quickly. Okay, so we said that we can deprotonate this oxygen here, which is going to leave us with this, right? A negative charge. Okay. Now, you may recognize this when we talked about, what is the word I'm looking for? When we talked about enolates, right? So, because we have a double bond and a negative charge, so double single bond, there's room for electron movement there. So this can go to that. So we have two different structures. What are you seeing here when I'm talking about electron movement? That's creating resonance. So these are two different resonance structures. The reason, well, I guess, I don't know what necessarily comes first. So because this is readily, this comes off, let me put this. The reason that it is so favorable for the hydrogen to be pulled off, for this to be deprotonated, is because the fact that you can have resonance. So this is a very stable state because the electrons can move, so that makes it easier to pull off the hydrogen, in a sense.
Resonance makes it easy for the hydrogen to deprotonate?
Yes, because we're talking about a very stable state here. Okay, so anytime you have resonance in like an intermediate or a transition state, that's going to make the reaction itself happen quick, more readily. Okay. Okay. The acidity of the carboxylic acid is affected by, I'm going to see if you remember it, but so the addition of electronegative groups and the distance between those electronegative, inductive effect. Very good. very important. That one will probably come up again. So essentially, this is our normal carboxylic acid. Do get used to this way of writing it, okay? Okay, I just wrote the pKa's. What are the pKa's telling you here? Which is the stronger acid, according to the pKa's?
The Fe.
Yes, exactly. So the lower the pKa, the stronger the acid. Good. So we've added 3 fluorines, so 3 electronegative groups. We see a drastic decrease in the pKa. So by adding these electronegative groups, we increase the acidity. Okay. The other piece of the inductive effect. This one's kind of hard to see, I guess. Okay, so we have 4.82. So this first one, we have more carbons than we do for, so we have acetic acid. Here we have 4 carbons, so this one would be
Like more or less acidic?
oh, sorry, the name. If this is a ethanoic acid, this would be
Butanoic.
very good. Okay, we can see that these have similar pKa's. This one's a little bit higher, but pretty close together, right? Here, we'd added chlorine, so an electronegative group right next to the carboxylic acid. We see a drastic drop, right? Not so much as having 3 fluorines, right? But still a pretty drastic drop. Here we've moved the chlorine to the farthest away carbon, and it's almost back up to where it was without a chlorine group. So inductive effect, the number of electronegative groups and the distance from the carboxylic acid. Is that all ringing a bell from earlier like last semester? Okay,
Yeah.
I figured.
So the number of electronegative groups and their distance.
From the carboxylic acid group, exactly. I'm gonna write it out down here just because it's a little longer. Okay, so now we're going to talk, that was the acidic side of a carboxylic acid. Now we're going to talk about the basic side. So carboxylic acids are only weakly basic, okay? They're really not considered a strong base at all, not even relatively strong. Okay, so in a basic situation, you're going to protonate the carboxylic acid. I do want to point out where you're protonating, okay? So you're adding the hydrogen to the carbonyl oxygen. You're not adding it here, okay? It's not going to look like this, okay? That's not going to happen.
And that's because in basic conditions, that acidic hydrogen can't pull off.
It's not going to be as likely to, okay? The basic conditions, or let me put it this way. When a carboxylic acid is acting like a base, that doesn't necessarily mean the condition is basic, but it's acting like a base. Okay, so typically that would maybe be in an acidic condition. So if you were to react this with an acid, okay, the carboxylic acid is going to, if this is a slightly stronger acid, it's going to force this one to act like a base.
Okay.
Okay. The reason that the hydrogen is not being added on this oxygen is because it's not able to, what's the word I'm looking for? Delocalize that positive charge. Okay. Essentially, this positive charge doesn't have anywhere to go. When it's here, there's room for that positive charge to move to the carbon and then move to this oxygen. But notice how the positive charge is always next to, when it's on an oxygen, is always next to a double bond. That allows the delocalization. If the positive charge is next to a single bond, there's no opportunity to delocalize, and this would be very unstable. This makes it more stable.
Okay.
So again, carboxylic acid, relatively strong acid, fairly weak base, but can technically act as both. When it's acting as an acid, it deprotonates on the hydroxyl oxygen. When it's acting as a base, it's going to protonate on the carbonyl oxygen. Make sense? Let's move into specific reactions.
So do you think he'd give us a specific reaction and ask to explain what's happening with that?
So with this chapter, I drew a lot of stuff on the board. I don't think you're going to see those types of drawings. I think he might ask you about how the carboxylic acid will react. Like, will it act like a base? Will it act like an acid? If it's acting like an acid, is it deprotonated or protonated? I see a lot of like circle the correct answer in that instance. When it comes to the specific reactions that we're going to talk about, really I think functional groups are up for grabs, and like what's the final product type thing. I'm trying to remember exactly. I know that on the midterm, it was either the midterm or the final, you basically have an entire sheet of functional groups, and you have to like match them to a list of functional groups. So I don't know if he's going to give you a taste of that on this quiz, but I know for sure that that came up on the midterm and or the final. Okay.
We missed class on Monday or Friday. We missed class on Friday.
Oh, why?
His car
Oh, no.
battery shot, so he couldn't make it in.
Jeez.
So he
I'm surprised he didn't, like,
flew.
walk.
He was like, my wife could have drove me, but I still wouldn't have made it on time. Like, okay. It's really fine.
So he kind of went quickly through these reactions?
Yeah.
Okay. Okay.
He went through all of these last class.
Okay. So essentially what we have here, we're running a substitution, okay? But to make that happen, we basically run two reactions. We run an addition reaction, and then we eliminate to get back our carbonyl carbon. So in the addition reaction, what happens in an addition reaction?
Something's added.
Something's added, but what has to happen before something can be added most of the time?
Oh, it's like deprotonated.
Well, not in this case. A hint. It has to do with this double bond.
Has to break.
Yes, the pi bond has to break, okay? That is pretty much universal for any type of addition reaction. So we're going to break this pi bond, and we're going to add something to the oxygen and add something to the carbon. So, I heard that. So if we're looking at the carbonyl group, because we know that's going to break, which end is a little bit more negative?
Oxygen.
Okay, making the carbon a little bit more positive. We have a nucleophile here bonded to a hydrogen. What charge is the nucleophile going to have?
The nucleophile.
Yeah, what charge is the nucleophile going to have?
Negative.
Negative, good. Because it's attracted to positive. Excellent. Meaning the hydrogen is going to be a little bit more positive. So by knowing that, we already know what's going to be added here. Okay?
It makes so much more sense when it's drawn out.
Yeah.
So much more sense.
So that's the first step. This is the addition. So the pi bond and the carbonyl group is broken. The nucleophile is added to the carbon, and the additional hydrogen is added to the oxygen. The second step is our elimination, which we know is just the opposite of addition, right? So we're going to remove two things, and that's going to drive a double bond to be formed. So this L is an L because it's representing our leaving group. So this L, we already know, wants to come off. This hydrogen is going to be removed, so we have the hydrogen and the L coming off. That's going to drive our pi bond to form again, except this time, instead of our leaving group, we now have our nucleophile attached. So we've run a substitution by running an addition and then eliminating it. This is Becker calling me. Hello? (1 p.m. today). So that means I don't have to go to class. Okay. This concept seemed pretty okay?
Yeah.
Okay. Really, there isn't a whole lot that you need to necessarily memorize from this. I think questions on this would relate more to where the attack is happening. Okay, so you already know where the nucleophile is going to attack here. You know what charges everything has. I would just know that you run an addition, then elimination, and the nucleophile is replaced.
Okay, so how do you know where the double bond's going to form again for the elimination?
I see what you're saying. So it has to do with where things are being taken off of, okay? Because that's going to kind of create the vacuum in a sense where a bond needs to be formed. So we know the leaving group is going to come off, okay? The H here is also fairly acidic because it's an alcohol group. We know that H is fairly acidic. So that H is readily going to come off. The nucleophile typically isn't going to want to come off. It just attacked, right? So that one wouldn't really come off. And breaking the carbon-carbon bond, that really doesn't happen without some sort of force acting upon it. So really these two are the only things that are going to come off. And so that would leave the oxygen with one less bond than it normally has and the carbon with one less bond. So that's going to drive the double bond reforming.
Okay. Is that going to make like a sub-product along with that?
The H and the L?
Mm-hmm.
I think it would depend on what the leaving group actually is. It could be like iodide, for example, which it may react with hydrogen. She didn't include that as like a subproduct, but I think it's fair to say chances are you're going to get some reaction there between whatever the leaving group is and the hydrogen. Most likely it's a halogen, so there will be some kind of secondary product there. Okay, the next few reactions, there's really not names to remember, okay? It's more of remembering that this carboxylic acid can be used to make a lot of different other functional groups. So the rest of these are all derivatives. So you start with a carboxylic acid group and you end up with very different final products. Okay, so I'll use both names because I think he's been using both names. So alkanoil. I'm more familiar with acyl, but alkanoil, I know he did that for like acylation, alkanolation.
Yeah.
Okay. So you take your carboxylic acid group, and you react it with something that has a halogen in it. So there's two different options that he gave. So you had, which is just thionyl chloride. Don't memorize that. Okay. Don't memorize that.
Okay.
Or phosphorus tribromide. Again, don't memorize that, but something that's carrying the halogen, okay? I would know these names just because that's really the only information you're given is what the two are reacting. So carboxylic acid group, something with a halogen, and you're going to have essentially just a switch, okay? So instead of ROH group, we would end up with this or this. So this is kind of a new functional group in a way. Know that you can, so I'm just going to put the X. I don't know if all halogens would necessarily do this. I'm assuming chlorine and bromine are the most effective or efficient. But essentially, anytime you have a halogen on the same carbon as a carbonyl group, you have an acyl halide. Okay? So here we have anhydrides. When you're creating anhydrides, and I think you might do this in the lab actually. I don't know if I'm thinking of regular chemistry. Can't remember. So we're going to react our carboxylic acid group with this. What did we just say this was?
Acyl halide.
Good, exactly. And this one specifically would be acyl chloride. I don't think he'd have you name them, but just know if he did miraculously ask for that, it's just you replace the name with the specific halogen name. Okay, so anhydride, we're actually going to remove our H and remove our chlorine. So imagine this being flipped. We're going to have the R groups on either side. So R carbonyl O. This O is going to bond to this carbon. Okay? So anhydride, if we look at this name, an means without or to take away or, hydride, hydrogen. So you're removing the hydrogen. You're removing the halide. Oops.
And this is all one process?
No, so this is two different ones. So anhydrides is a separate reaction. So you can, from a carboxylic acid, you can create an acyl halide. If you react those two, then you can get an anhydride.
Oh, okay.
Again, he doesn't get into the details of the mechanisms of these reactions. It's more of just understanding how we get from here to here, or the fact that you can get from here to here.
Right.
Okay.
And there's no catalyst used for these?
I know that in some further ones, there is like heat may be added for the intramolecular ones. Some of these, when we get to the ones where you'll see there's amines or ammonia used, that would be considered like a catalyst in a sense. In these ones, it's not specified. You might want to refer back to the notes, but you know, I typically try to go from Dr. Cosper's notes and then if there's changes, but she doesn't make any specific mentions. Okay. So we just talked about anhydrides. You can also make cyclic anhydrides. So I know I've written this a little, you know, it's not in your typical straight chain form. Do you recognize that functional group? Or the combination of functional groups?
The
Dioic acid. So to do a cyclic anhydride, you need to have 2 carboxylic acid groups on the same compound. We can kind of see here that the chain is going to fold in on itself to make a ring. That's pretty typical of any cyclic or intramolecular process. This is one of the ones where you do have to have heat. That may be something that he asks about. But when you heat this, we're actually going to remove water. So we still see our anhydride group. It's just in a cyclic product now. There is, oh no, I'm thinking of a different one, sorry. I was going to say there's another name for these. That's something else. So cyclic anhydride is an intramolecular process. You start off with a dioic acid. You heat it, so you are essentially just dehydrating it. When water is removed, you end up with a cyclic anhydride.
So anhydrides, they don't have carboxylic acid groups?
No, so this is a different functional group that doesn't have the carboxylic acid group.
And that's because the O is missing the hydrogen.
Exactly, yeah. So because this O is being shared, there's no way to have the OH group that's seen in a carboxylic acid group. Exactly. Okay. The next one you should be familiar with, esterification. What happens in esterification? Okay. Obviously, one of the reactants is a carboxylic acid. We're talking about it. What does a carboxylic acid react with?
Alcohol.
Okay, good. So you know this one for sure. So we have...
That was right off the top of my head. I can't believe I got that right.
Don't say that. Act like you knew it all along. Okay.
Chapter 8 last semester.
Mm-hmm.
I don't know why I know that.
So in esterification, we're going to remove the OH group from the alcohol. We're going to remove the H from the carboxylic acid. So again, we're removing water in this case. The oxygen is going to bond to the alkyl group from the alcohol, creating our ester. So I am going to put that one on here, even though we've talked about it before. It's still a functional group you should know.
So the ester is the COC.
COC, exactly.
Okay.
or C-O-R. I'll do R just so it's a little bit more universal because he could do it either way. But yes, carbonyl group, OC. Be careful getting that confused with ether, right? No carbonyl group. Okay.
Why didn't he just say that? He made that so much more confusing in class.
Esterification?
Yeah, he never said it was esterification.
Oh.
He made it sound like it was a whole different thing we've never learned before.
Oh, no, you have learned it before. I noticed that in her notes as well, she didn't use the word esterification, even though in previous chapters, I'm pretty sure she did use it.
Yeah, it would have been so much easier that we already learned it.
Yeah. Okay. So, this is the point where we get to having different names for cyclic compounds that have the same functional group in them. So, we had anhydride and then we had cyclic anhydride. So now we're going to talk about cyclic esters, but they have their own name that you have to know. They're referred to as lactones. So if I told you this was intramolecular, you know there's only one molecule involved. So what two functional groups have to be present on that one molecule for this to take place?
Is it, okay, no, it's forming an ester.
So we just talked about esterification.
So it doesn't have to have alcohol and carboxylic?
Exactly. So, and it's going to be on either end, right? Because they're going to react together. So we're going to have our OH group here.
Should I know hydroxy acid?
I would. But you just made the connection that all that means is a hydroxyl group and a carboxylic acid on the same thing. Right? So you know what's there, now you just have to memorize the name.
Yeah.
Okay. So the important thing with this reaction, it's only going to take place if the final product makes a 5 or a 6 membered ring. Why would it only be 5 and 6 membered rings? Why not a 3 membered ring?
Because they're more stable.
Exactly. So the confusing part with that, and again, I don't think he would necessarily ask you this question, but that doesn't necessarily mean 5 or 6 carbons. So we have 1, 2, 3, 4, 5 carbons. This is actually going to make a 6-membered ring, and I'll show you how that happens. So again, it's the same process. We're going to remove the OH group, remove the hydrogen, and this O is going to react there. So it's going to fall in on itself, okay? It's going to end up looking like this. So we have a 6-membered ring when we only have 5 carbons because one of the members is going to be this O. Not that I think he would get that picky, but just be aware, doesn't necessarily mean 5 or 6 carbons. 6 carbons would actually make a 7-membered ring, so that wouldn't take place. Just a thought. So we still see our ester group, carbonyl group, OC. So lactones.
Now, is there a specific way to name those?
Don't worry about naming. Don't worry about naming. You will find that there are some functional groups that you never talk about naming. You'll be grateful for them. Not too scary, right?
No, I don't think I just have to memorize them.
It'll take time. I think, like I said, a list with pictures can be really, really helpful.
Yeah.
Okay. This one you may or may not be familiar with from regular chemistry. I think it depends on who your professor was. Amides. Any familiarity with amides?
Except there is an N.
Okay. So some people might get this confused with amines. Okay, they are very closely related. We're actually on the last page of chapter 19, just kind of going through the carboxylic acid derivatives. For all of these, I think the big focus still on the reactants, what's being reacted, but you're going to see a lot of new functional groups, right? So we're talking about how the functional groups are formed, and just work on memorizing those. If you haven't already, I would work on making like a comprehensive list of these, because there's a lot of them. Okay. So we have our carboxylic acid, and we're going to react it with an amine. An amine is actually a derivative of ammonia. All you do to get from ammonia to an amine is add a carbon. So we're going to replace at least one of these hydrogens with an amine. So it ends up looking like this is just one example, but so the nitrogen has 2 hydrogens now and is attached to a carbon.
So it'll always be NH2.
Not necessarily. She doesn't specify what. So it could be, let me make this more inclusive. It could be any of those.
Okay.
So it's primary amine, secondary, tertiary. There are no notes that would say, you know, only a primary in this case. So it could be any type of amine as far as I know. So the difference between an amine and an amide have to do with having a carbonyl group bonded to the nitrogen instead of just a carbon. So our final product would look something like that. So if this was the one that we used, we see that we're dropping a hydrogen. We're going from 2 hydrogens to only 1. And that nitrogen is then bonding to our carbon. So we're removing a hydrogen, and we're removing the OH group. So technically, we're just removing water here. OH group, hydrogen. So actually, now that I'm looking at this, I see that we would not be able to do this with a tertiary amine because we can't remove a hydrogen. So primary or secondary in this case. If we were to do this with a secondary, again, I don't think this will necessarily be his focus, but just so you're... It would look like this. So the final hydrogen is removed. The N bonds to the carbon with the 2 R groups. Okay. So ammonia, NH3. And just for clarification, NH4 plus, ammonium. Yes. So this is the ammonium ion, a longer word for more hydrogens. That's how I remember it. So ammonia, N with 3 hydrogens. Amine, an N with at least 1 carbon, up to 3 carbons. Amide, carbonyl group bonded to the nitrogen. So not just any old carbon, it has to be a carbonyl group.
Okay.
So
Did you hear the Smith close?
we did, yeah, we just got the message.
Yeah. That's really stinks. I got out of the test, so I'm happy about it.
Hey, Kelsey. Okay, so I did put just the 3 different variants. Just know that it needs to have at least 1 carbon, 1 R group, to be considered an amine. And here, again, the N group has to be bonded to the carbonyl group directly to make an amide. Okay with these two? Okay. We can do a quick kind of review of the top two since you weren't here, Jocelyn. So obviously carboxylic acid, one to know. The rest of these, other than ether, so these are all considered derivatives of carboxylic acids. So you can start with a carboxylic acid and lead to at least one of these. So when a halogen is directly bonded to that carbonyl group, it's referred to as an acyl halide. Acyl, you might remember from Friedel Crafts acylation, right? Or I know he's also using alkanoil. Same thing. So alkanoil halide is the same as an acyl halide. Don't let that confuse you. When we take a carboxylic acid and we react it with an acyl halide, we end up with something called an anhydride. Okay, so essentially we remove the halogen and the hydrogen. The carbon is then bonded to this oxygen, and you have an anhydride functional group. Ester was brought up last semester. You have your carbonyl group bonded to an oxygen that is bonded to another carbon. This occurs by reacting a carboxylic acid with a alcohol group. We'll skip over ether. I just put that one to make sure that you don't get the two confused. You can also make cyclic esters. The term for that is a lactone. You will want to know that. But essentially, you have one molecule that has both a carboxylic acid group and an alcohol. They react together, forming a ring. Your lactone. Okay?
The lactones come from, oh yeah, the cyclic.
Okay. Yeah, so it's essentially it's called a hydroxy acid. So on one end you have your carboxylic acid group, on the other end you have an alcohol, and the two ends react together. Okay. How are we feeling about amides? Okay. Another nitrogen derivative, amides, which you may remember if you, I don't know, we did talk about this last week, I think. Okay, we used this one in another example when we were talking about anhydrides. So here we have butane dioic acid. Dioic because we have two carboxylic acid groups. Now, when we just heated this, we removed water and we made a cyclic anhydride. If we heat it in the presence of ammonia or amines, so if we heat it in the presence of nitrogen, we end up with this.
He kept talking about in class, like, things are reversible. So, like, in ester, they're reversible,
Yes.
and then he, like, talks about the steps of them.
He did talk about the steps.
He said protonation, nucleophilic attack on the carbonyl, tetrahedral intermediate, and then water.
Yeah, so pretty much if you look at, on the second page, 19.7, so you have substitution at the carboxy carbon. That's essentially happening in a lot of these, okay? So the carbonyl group, you have some sort of an addition and some sort of a elimination. So the type of attack that he's talking about is just based off of the nature of the carbonyl group. In reality, I mean, he could definitely ask you questions about that. I think you're going to see a lot of questions about the functional groups themselves. I know Dr. Cosper did mention some of these were reversible, but she didn't necessarily indicate that for all of them. So I would refer to his notes. If he says something's reversible, maybe take note of that.
He said for amides, I think it was under the same like coding that he said. If
Yeah.
hot acid or base favors reversal. I don't know if that's.
Oh, I see. For amides?
Yeah.
Okay. I do know, and this one does mention heat as well. It doesn't necessarily go into that much detail. I obviously can't remember exactly what he quizzed us on, but it's up for grabs. I don't necessarily seeing that be the primary focus of the quiz questions. But if he does make mention of it, I would, kind of file that away just in case.
Okay.
But, okay. And didn't mention that this was a cyclic amide, but okay. So I'm going to make it a little, this is technically a cyclic amide, even though it doesn't necessarily say that in Dr. Cosper's notes. So I'm just going to make reference of what an imide is. Okay, so we have a nitrogen with 2 carbonyl groups coming off. Okay. So we talked about esters and how they can form cyclic compounds called lactones. You can also make cyclic amides. These are referred to as lactams. There's an M in amides. There's an M in lactams. That's how I remember it. So what 2 things need to react to make an amide?
The carbon and the nitrogen.
More specifically, sorry, the functional groups that need to react.
Oh.
Where does the carbon come from?
The
Carboxylic acid, right? And the nitrogen comes from amine. Yep. I actually don't know if it's amine or amine. Okay. So we have our carboxylic acid group on one end. On the other end, we have our nitrogen bonded to a carbon, so our amine. Again, very similar to in a lactone. We're going to, this is under heat, so we're going to dehydrate it. So we're going to remove the OH group here and one of these hydrogens. The carbonyl group is going to react with the nitrogen. So again, we retain the carbonyl group. One of the hydrogens has been removed, so we only have NH here. But here we have our amide functional group, so our lactam. That's the last carboxylic acid derivative, okay? The last 2 reactions, one is really review. So let's go over that one first. So if we have a carboxylic acid, and we reduce it to its fullest state, so fully reduce it, what would be your final product?
Alcohol.
An alcohol. More specifically, a primary alcohol, right? So that's always going to be the case. And remember that this goes the other way. We've talked about it more so in the, when we're talking about oxidation. So a primary alcohol that's fully oxidized or over-oxidized, you end up with a carboxylic acid. It is mentioned here, and I know we had talked about it in other, I think last semester. So the reducing agent used here, lithium aluminum hydride. Did he reference that in class? It's a very strong reducing agent. That's the only reason why I would mention it. So that may come up. Definitely knowing that this can go back and forth. The next one is the only reaction that has a name that you need to memorize.
What's the hydronium used for as a reagent for that reduction?
Oh, the H3O plus. I'm assuming that's just referencing an acidic environment. So there's some type of acid present. There aren't any notes on it. I don't know if he mentioned it in class. But typically when you have something like that, that's just saying acidic environment. The top one is talking about the reagent that's used. So I think that's all that it's mentioning. Okay, Hell-Vollard-Zielinski reaction. Essentially, this is just specifically bromination or a halogenation of the carboxylic acid. This differs from the other reactions because the reaction site is not on the carboxylic acid or the carbon, it's on the alpha carbon. So if we remember our terminology, I'll use the example from Dr. Cosper's notes. The alpha carbon is this carbon here, okay, the carbon next to the carbonyl carbon. The notes do mention that you're reacting in the presence of a very small amount of phosphorus. I don't think that's something that you necessarily need to know, but essentially it makes phosphorus tribromide, which we did talk about when we were talking about acyl halides, but I don't think that's necessarily the main point here. So the bromine is added to the alpha carbon, so it doesn't actually involve the carboxylic acid group directly. It also doesn't say if there are multiple halogenations or if it's just the one. The example specifically shows one, so I think only one is added. So Hell-Vollard-Zielinski essentially is just halogenation of a carboxylic acid at the alpha carbon.
And it makes phosphorus tribromide?
So that's the confusing. So essentially, you have bromide, and you have a little bit of phosphorus, like trace phosphorus. These react to make phosphorus tribromide, which then reacts with the carboxylic acid. I don't think that should be your main focus here, but that's just what the notes mention. So you don't add phosphorus tribromide directly for some reason, but it can occur when you have a little bit of bromine and a little bit of phosphorus.
So it's still a carboxylic acid. It just has a bromine on it.
Yes. Yes.
Okay.
That all makes sense? Okay. And you've just gotten through chapter 19?
Yeah, we
Okay.
haven't started 20 yet.
Okay. I'd probably rather wait to go over it until you guys have gone over it so we can go over it next Tuesday. I can go back to the beginning and just kind of talk about the stuff that you missed, Jazz. Do you prefer Jazz or Jaslyn?
Doesn't matter.
Okay, all right. We can start out doing some more naming. Amber, I don't know if you want to hang out and do some more of that. Or you can go home because you don't have anything going on.
They already told me not to go into work. They were like, just don't come in. Because I work at 1. So
So yeah, no, obviously not.
Or
Go.
is it noon? I don't ever remember.
It's okay.
I'm always-
Obviously not necessary.
Yeah.
Okay. So our carboxylic acid group, obviously know the carboxylic acid, be able to pick it out in a molecule. I don't know if you had gotten back from your lab at this point. We did talk a little bit last week about what functional group takes highest priority when you're naming. I don't know if you were here yet. So for example, if we had something like this, where you have multiple different functional groups in the same molecule. When you're going to number them, okay, you want to make sure you know which one takes highest priority because you want to make sure that one has the lowest number. So that all has to do with how oxidized that functional group is. Okay, so oxidized, electronegative, but essentially oxidized is probably the easiest way to remember it. So we have 3 functional groups. We have an alkyl group, we have an OH group, and we have a carbonyl group, specifically a ketone. So which one of these is the most oxidized?
Not the hydroxyl?
Not the hydroxyl. It's actually going to be this carbonyl group, and that's because there's 2 carbon-oxygen bonds. Here there's only 1 oxygen or a carbon-oxygen bond. So we would want to make sure that when we're naming this, we give this first priority, okay? This relates to carboxylic acids because essentially at this point, it's always going to be first priority. So the carboxylic acid carbon is always going to be carbon number 1, no matter what else is on there. In terms of naming, I know he mentioned some common names as well as the IUPAC. We'll go over IUPAC first. So how would we name this molecule?
Well, butane.
Okay, good. So there's 4 carbons. How do you get from butane to a carboxylic acid name? What's the ending? OIC. Good. So we're going to drop our E. Butanoic acid. Okay? So perfect process through that. Number of carbons, drop the E, add oic acid. Do we have to say where the carbon is or where the carboxylic acid group is?
Well, no, because it's first priority.
Right, and it's first priority, and because it's always terminal, it's always going to be number 1. So that would be redundant. So you're right, you don't have to put a number here when you're naming carboxylic acid groups. When we are talking about common names, there are 4 different prefixes. Some of them are pretty close, but some of them are pretty different. So form, like formic acid, applies to only 1 carbon. Acete is 2 carbons. Propion is 3, butyr is 4. When we're talking about this chapter, the one that you're really going to need to know and feel comfortable with is acete, because acetic acid is very common, it's used very often, and in industry you would never call it ethanoic acid. You would just call it acetic acid. So he wants you to be very comfortable with that.
Oh, okay.
So that's the only one that I would say you have to know. He doesn't normally ask the other common names. He's happy if you know IUPAC. This is the one instance where you need to know the common name of something. Okay. What do you think about this one, if I ask you to name it?
What's cyclic?
Cyclic. If we had just this, there's a special name for this.
Oh yeah.
What's the B?
Oh, I can't think.
Benzene.
Benzene, yeah.
Okay. So this alone is benzene. When we add this functional group, you're going to remove the ene, which is slightly different than what you did over there, but it's the same ending. Okay, so benzoic acid. I think this was reviewed in the first chapter, when you first chapter of the semester. I would say you should feel comfortable with any type of benzene derivative. So adding an aldehyde group, having a ketone, or more so aldehyde. Then there are some other ones, but so benzene with the carboxylic acid, benzenoic acid. Or benzoic, I think I said benzenoic. All right. I think I mentioned this for another example. So we have 2 carboxylic acid groups. This is considered to be under a class of compounds called dioic acids. Similar to diols, right? So 2 carboxylic acid groups. In terms of naming, I don't know if he would have you name a dioic acid, but it's really not that much different than a typical carboxylic acid. So again, we still only have the 4 carbons. So butane. Instead of adding ioic, you're just going to write dioic. So butane dioic acid. Some physical properties that you should be aware of. So is this functional group polar or nonpolar?
The OH?
The whole thing.
Oh.
Polar or nonpolar? You said polar?
There's one.
Oh, sorry, I thought you said polar.
Oh.
So yes, it is polar. So oxygen is more electronegative than carbon and hydrogen. So we have a lot of dipoles here. So this oxygen is going to be slightly more negative, carbon more positive, hydrogen slightly more positive, oxygen slightly more negative. So definitely polar. We've got a pi bond here and our double bond. So there are some addition reactions that we can do there by breaking that pi bond. Would this carbon be sp, sp2, or sp3?
sp2.
Okay, good. And keep in mind this hydrogen readily falls off, meaning that's it's a very acidic hydrogen. Can you name this carboxylic acid for me? Propanoic, very good. Do you think this would be soluble in water?
No, because extra carbons.
Okay, so we know that part of that is polar, but we don't know how much that has an effect. Okay, so when we're talking about alcohols, if you think way back to last semester, any type of alcohol, 1 through 4 carbons is soluble. Same thing with carboxylic acids. So if we had pentanoic acid, that would be insoluble. But 1 through 4 is completely soluble. Okay, so I have 4 different molecules up here. Or I'll do, we're going to rate their boiling points from lowest to highest boiling point. Okay, which one of these, A, B, C, or D, do you think has the lowest boiling point? Okay, why?
No hydroxy.
Okay. Think of in terms of intermolecular reactions. What type of intermolecular reactions can those types have? What are the 3 types of intermolecular reactions? London dispersion, van der Waals, those type. So we've got London forces, which are also, you might hear dispersion or van der Waals. Do those ring a bell at all? Okay. And then we have dipole-dipole. And then we have hydrogen bonds, which is actually a type of dipole-dipole. Okay. So you are absolutely right. The alkane does have the lowest boiling point. The reasoning behind that, okay? So because alkanes are nonpolar, right? There's just carbons and hydrogens, no electronegative groups. The only type of intermolecular force they can have is London forces. So these are very weak, temporary forces that allow for slight attraction and then they go away. So you have a little bit of attraction and then it stops. Which one do you think would come next?
Either A or D.
A or D. Okay, those are close. So it's actually A, and let's talk about why. So the rest of these all have oxygens. So now these are all polar. So it becomes a little bit more difficult. So really what we have to identify is which one of these are able to make hydrogen bonds, because hydrogen bonds are the strongest intermolecular force, okay? So hydrogen bonds, well, let's talk about dipole-dipole. So dipole-dipole is anytime you have an electronegative molecule or an electronegative atom in a molecule. So for example, if we had hydrochloric acid, okay? We know that Cl is going to be more negative, H more positive, and we can get similar charges to make an attraction, right? Hydrogen bonds are a specific type, and it's anytime you have nitrogen, oxygen, or fluorine bonded with a hydrogen, okay? Water is a really great example, okay? Other water molecules are going to be attracted and can make hydrogen bonds, okay? So if we look at the final 3, the difference between our aldehyde, and our alcohol is one of these can make hydrogen bonds and the other one can't. So if we look here, we have an electronegative group. Do we have hydrogen bonded to nitrogen, oxygen, or fluorine in our aldehyde?
No.
No. So no hydrogen bonds.
Okay.
If we look at our alcohol, do we have a hydrogen bonded to a fluorine, oxygen, or nitrogen? We do. So this one can make hydrogen bonds, which is why it has a higher boiling point. Okay? Now, looking at C, we have an OH group. So this one both of these can make hydrogen bonds. But what makes this one different from this one?
The carbonyl group.
What was that?
The carbonyl group.
Yes, but more specifically, it allows for 2 hydrogen bonds versus just the one. So let me erase this. So if we have our alcohol, so our alcohol, we can make a hydrogen bond there, right? If we have essentially, we make it possible for 2 hydrogen bonds to form. This is referred to as a dimer, or a hydrogen bond dimer. So this one, only 1 hydrogen bond can form. This one, 2 hydrogen bonds can form. So that's what makes this one have a higher boiling point than this one. Just for reference, so we've got, obviously, the alkane, very, very low. Aldehyde has slightly higher, well, significantly higher, 21 degrees. Alcohol, 78.5, over 118 degrees. So if we were thinking to water, right, because we know water has a very high boiling point. Water has 100 degrees Celsius boiling point. This is the first molecule that you've been introduced to, really, that has a higher boiling point than water. Okay? So again, not that you would necessarily get asked on the specifics of this, but in terms of physical properties, it's up for, it's definitely kind of in the ring that he could ask questions about these types of interactions or things relative to others. So he might ask you to compare a carboxylic acid and an alcohol in terms of boiling point. Okay? Does this make sense? Mm-hmm. Yeah, Amber?
So do dimers have an even higher boiling point than regular carboxylic acids?
So it's not that, so that's not, these aren't bonds. They're attractions.
Oh wait,
So,
not a dimer. I meant a diatomic.
Do you mean dioic?
Yeah.
So if you had a dioic acid that had the same number of carbons as a singular carboxylic acid, the dioic should theoretically have a higher boiling point. I don't know how much higher, but technically you would be able to have more hydrogen bonding.
Because wouldn't that be like 4 hydrogen bonds?
Yeah, yeah,
So that's like
yeah.
pretty significant.
I don't know how much higher it would be, though. That's a good question, though. Something to look into. Okay. When we look at a carboxylic acid in the NMR, would the carbon and hydrogen be shielded or de-shielded?
De-shielded.
Why de-shielded?
Remember he said it in class,
Yes, whenever you have an electronegative atom next to a carbon or a hydrogen, that's going to pull electrons away from it and pull electrons away from the nucleus, de-shielding the nucleus. So it basically takes that electron protection so the molecule can get pushed farther downfield. Good. So carboxylic acids can technically act like an acid and act like a base. They're definitely more acidic. I mean, acid is in their name, but they do have some basic characteristics. So when we think of acids and protons, what do acids do with protons? Do they donate them or do they accept them? They donate them, exactly. So we're going to deprotonate. Okay, so we're going to remove this hydrogen. When we do that, it leaves a negative charge, right? Now, because we have a negative charge and we have single and double bonds next to each other, this allows for electron delocalization. What sort of stability comes from electron delocalization? Starts with an R. Resonance. Okay, so these are resonance structures. Okay, so, and this is really why the fact that resonance is available, or how do I put this? I always have a hard time wording this. Because this is stabilized by resonance, okay, that promotes the hydrogen being removed because the intermediate that's formed here is very stable. Okay, so having stable ions makes the ions more readily formed. Does that kind of make sense? Okay. So let's see. Okay, good. Relatively strong acids, but not necessarily considered strong acids themselves, okay? But relatively strong. And their acidity is affected by something called the inductive effect. Do you recall that from last semester?
Mm.
Could you describe what the inductive effect is? Okay.
It says a carbon next to an acidic carbon and their electronegativity the hydrogen depends on their pKa's.
It's a pretty complicated way of saying what I think is a little bit more simple than that. Okay, so there's two parts to the inductive effect. Okay, the first has to do with the number of electronegative groups present. Okay, so one thing, I don't know if he uses this, but be comfortable with this notation. This just means carboxylic acid. I don't know if you've seen that before.
Yeah.
Okay, so here we have acetic acid. Okay, so we just have two carbons, no electronegative groups, and here's our pKa. Here we have 3 electronegative fluorines, and we see a significant drop in the pKa. According to the pKa, which one of these is a stronger acid? So it's an inverse relationship. The lower the pKa, the stronger the acid, okay? So a little bit of review from last semester. So this one is considered the stronger acid. So by adding electronegative groups, you make it more acidic, okay? So that's one piece of the inductive effect. The second okay. So here we have 3 different molecules. The first one has now 4 carbons, so it's butanoic acid, no electronegative groups. So we've just really added carbons onto this. The second one, we see a chlorine right next to the carboxylic acid group. And in this one, we haven't changed the number of carbons, but we moved the chlorine all the way to the end, so as far away from it as possible. So we see with no chlorines, no electronegative groups, our pKa doesn't really change much, okay? When we add the chlorine very close to the carboxylic acid, it drops it significantly. Not as significant as having 3 right next to it, but very significantly. When we move it all the way to the end, it brings the pKa back up to almost its original place. So the inductive effect has to do with the number of electronegative groups and the distance between those groups and the carboxylic acid. The more groups you have and the closer they are, the lower the pKa and the more acidic it is. Do you want me to say that again, or did you get it?
No, I got it.
Okay, good. It's a long sentence. Okay,
I got
so
the gist, though.
good. So inductive effect, definitely have that one. That one's up for grab in terms of questions. So this is when a carboxylic acid acts like an acid. So let's talk about what happens when it acts like a base. So if acids donate protons, bases must accept them. So I'm going to write down the different option or the different forms, and then we're going to talk about why it forms that way. Okay. So we're reacting the carboxylic acid with an acid, and so that means we're going to protonate. So we're going to protonate at a specific place, and it's going to be this carbonyl oxygen. It's not going to be this oxygen, okay? So when we protonate, we obviously get a positive charge here. Again, because we have this positive charge and the orientation of the double and single bonds, we can delocalize that positive charge throughout the oxygens and carbons. I do want to point out there's a reason that it protonates there. It will not protonate at the hydroxyl oxygen. That won't happen. Okay? Essentially, when it does that, it can't delocalize the same way, so it's not as stable. Okay? So it's always going to protonate here, but the positive charge can be delocalized. But you'll notice the positive charge is always with the double bond when it's with an oxygen. It's never on the single side.
So we got rid of the double bond in the second, in the middle of that.
Right, so the charge has been delocalized to the carbon, so there really isn't any double bonds there, exactly.
Okay. Oh, all right.
Make sense? Okay. Let me just make sure I didn't miss anything. Again, weakly basic. Not considered a strong base whatsoever, definitely more acidic, but it can act like a base, and this is what happens when it does. Not a lot to worry about for this piece, at least.
I actually have a question.
Yeah.
When you brought up like the London forces and
Yeah.
So are the London forces more stable, right? Is it flip, or is it the hydrogen bonds are still stable and then?
So the hydrogen bonds are the strongest, and they make it's difficult with stability because typically when you're talking about stability, you're talking about bonds within a molecule, intramolecular. Hydrogen bonds are inter, and they're stronger. So there is a form of stability there, but I would be hesitant to use that word specifically. Yeah. But strength in terms of intermolecular forces, you can think of as stability. So the more strength, the more stable that attraction is. Okay, good question. Okay, so the next piece is the addition-elimination reaction, which is really just the general.
Yeah. He like went over it in class and it kind of made sense.
Okay.
I just didn't. He just kept saying tetrahedral, and I was like.
Okay, interesting. Okay, I didn't really make that. Not connection, but I didn't really emphasize that, but we can definitely talk about that. Okay.
Is it the hydroxyl, the poor leading group?
Yes. So we know that from. I think think it was chapter 11 or 12 last semester. For an OH group, a hydroxyl group, to be a good leaving group, you have to protonate it and make it an OH2 plus, so an alkyloxonium ion. In general, though, so if we do have a good leaving group, okay, we're just going to indicate that with an L, okay? When we're looking at the carbonyl group, which side is going to be more negative again?
Oxygen.
Good. Carbon more positive. What charge does a nucleophile have?
Neutral.
Not neutral, careful. So nucleophile. So phile means to like,
Oh yeah.
okay? Nucleo meaning positive. So it likes positive charges, which means it must be, well, do positive charges attract or repel? So if it likes positive charges, it actually is negative.
Oh.
The thing
Oh, yeah,
magnets,
okay.
right?
Like
Right?
loose bases,
So-
okay.
The names are tricky when you're talking about is it what it's attracted to and what it actually is.
Okay.
So our nucleophile is actually going to have a negative charge. So just by looking at these charges, you can kind of see where the reactions are going to take place. So the positive hydrogen is going to be attracted to the negative oxygen, nucleophile attracted to the carbon. So we are running an addition reaction. This is an addition elimination. So the first step is addition. In an addition reaction, we always break a pi bond and add something to each atom. So we have our oxygen, which is bonded to our hydrogen, and we have our nucleophile bonded to our carbon. So this is where he's coming up with tetrahedral. So we can see we have a carbon with 4 different attachments. So that's where the term tetrahedral keeps coming up. So the intermediate in this case is tetrahedral versus, I talked about the orbital hybridization. I didn't talk about the shape. What's the shape? So we said it's sp2, but what's the shape of this? Trigonoplanar. Very good. So we're going from a trigonoplanar shape to a tetrahedral shape. Okay, so that's addition. Then we're going to run an elimination reaction. Now, elimination is just the opposite of addition. So you remove something from 2 adjacent atoms, and that forces a pi bond to form, a double bond to form. So, by design, we have a leaving group here. So we have something that's going to readily want to leave. Okay? So the leaving group's going to come off. We also have an alcohol group where we know alcohols can deprotonate, so that hydrogen is going to be removed.
Yeah, I have here like with the base, it deprotonates.
Exactly, right. So when we take off the leaving group and the hydrogen, that's going to force our double bond to reform between the carbon and the oxygen. So we get our carbonyl group back, but instead of our leaving group, we now have our nucleophile. So we've substituted the nucleophile for our leaving group.
We substituted what?
Our nucleophile
Okay.
for our leaving group.
Gotcha.
Yep. So addition makes a tetrahedral intermediate. Elimination removes the leaving group and the adjacent hydrogen. Replacing. And we're back to our trigonoplanar, right?
Oh yeah.
Okay. The last 2 pages are all about our functional groups that we talked about. Again,
We talked about the complicating factors
for
of the like addition and elimination stuff, and I think he only said the hydroxyl is just a leaving group, and then the solution is
has to be basic to deprotonate.
I don't really know.
Okay.
Alkyl acid halide adding something. Oh, he brought up SOCl2.
So that is the next piece.
Oh, okay.
Derivatives. Okay, so he might be referring to that.
Gotcha.
But yes, OH is a poor leaving group. You would have to protonate it which I think what he's trying to say there is that's why the OH doesn't leave, right? So what's forcing the leaving group to leave and not anything else? I think that's what he's pointing to. So the OH itself is not a good leaving group. You'd have to protonate it for that to even remotely want to fall off. It's really difficult to break a carbon-carbon bond, and the nucleophile just nucleophilically attacked the carbon, so it's obviously attracted. So really it's down to these two, and oxygen, or OH, is a poor leaving group. So I think that's why he's making that, like, reference. Okay.
I mean, yeah, I can just look back at the video too. Like,
Oh, right, yeah. Okay. Okay. How are we doing on time?
do you mind if I actually ask you a question for my lab report?
Oh, yeah, no, of course.
I feel okay with this chapter.
Great. I'm just gonna pause.